first two kind of defects, the zero-dimensional defects and the one-dimensional defects. In the zero-dimensional, the vacancy, interstitial substitutional defects, and in one-dimensional, the line and the screw dislocations, the screw and the edge dislocations. We are done with that. Now we are moving towards the understanding of planar defects in solids, that is the 2D defects. Uh, External surfaces is one of the defect. External surface, one of the most obvious boundaries is the external surface along which the crystal structure terminates. Now, if you remember the definition of defect, uh, defect is a disruption in the perfect crystalline order. So as soon as this surface finishes, this surface or this surface or this surface, any surface, when it finishes or it terminates, it is basically disrupting the perfect crystalline order. All right. So external surface is the first kind of defects. And now how? Surface atoms are not bonded to the maximum number of nearest neighbors and therefore in a higher energy state than the atoms at the inner position. So if you have, let's say, these atoms located somewhere inside the surface, and this is basically your surface. So an atom which is situated over here in the center, it would have an atom situated in this direction, in this direction, in this direction, in this direction. So it would have the maximum number of nearest neighbors possibly it could have, and it would be balancing the forces that it would have acting upon this atom would be balancing each other. But an atom that is situated over here just close to the surface, it would be pulled by this atom, by this atom, by this atom, but there would be another atom, fourth atom, which is present in the case of the central atom, is missing in the case of atom which is situated near to the surface. And that's why this atom would be in a state of higher energy than the atoms in the inner position. Is this point clear to you?
Yes, sir.
All right. As a result of this, the bonds of these surface atoms that are not satisfied, they give rise to surface energy. So the surface energy that you have been uh, familiar with, it is basically due to this uh, imbalance in the number of nearest neighbor atoms that are there for the surface atoms. That gives rise to the surface energy, which is expressed energy per unit area or joules per meter square for the surfaces. Now, the second kind of planar defects, as I had already mentioned, are the grain boundaries. As it says, another interfacial defect is the grain boundary, and it is a boundary that was introduced to separate two small grains or crystals having different crystallographic orientations in a polycrystalline material. So obviously you cannot have this grain boundary in a single crystal.
एक्सक्यूज मी सर
G.
सर
सर आप
सर
स्लाइड चेंज
हमारे
कर
पास
रहे हैं?
सिर्फ प्लेनर डिफ्लेक्शन सॉलिड शो हो रहा है और वो भी इनकम्प्लीट स्क्रीन के साथ
और सर आप
Planar defects in
आपका
solids.
माउस इधर उधर होगा सर.
All right, let me share it again and see if it works with this. So, by the way, my voice is clear to you guys?
यस सर योर
यस
वॉइस
सर,
इज क्लियर
स्लाइड भी आ गई
Yes,
और
sir.
वॉइस भी.
Is it better now?
सर नाउ प्लेनर
यस
डिफ्लेक्शन
सर.
सॉलिड्स है ठीक है यस सर
Okay, all right. So we have looked into one kind of planar defects, that is the external surfaces. The other kind of planar defects is essentially grain boundaries. Grain boundaries, as you already know, it is the boundary which is separating two small grains or crystals having different crystallographic orientations, again in a polycrystalline material. You cannot have it in a single crystal because single crystal would essentially have one grain present. Now, if you look at the image onto the right hand side of the screen, you would see that this is essentially a grain boundary, then this is grain boundary, and if you see within the boundary region, which is probably just several atomic distance wide, there is some atomic mismatch in transition from crystalline orientation of one grain to an adjacent one. So if you see within this grain number 1, you have the atomic orientation in this direction, and within this grain number 2, you have the atomic orientation in this direction. And between these two orientations, you have a angular distance or a mismatch. Similarly, if you see this third grain, the third grain has an orientation of this direction, and the second grain, as I already mentioned, has an orientation of this direction, and there is a mismatch in the crystallographic orientation of the three grains. So, various degrees of crystallographic misalignment between adjacent grains are possible. You could have when the orientation is very small or a slighter order on the order of few degrees, then the term small or low angle grain boundary is used. So this grain boundary, if you compare the angle over here and if you compare the grain boundary over here, the angle, this angle, you could refer to this grain boundary or you could refer to this grain boundary as low angle grain boundary, and this grain boundary could be referred to as high angle grain boundary. All right, is this clear to you?
सर ये हमें किस तरह पता चल रहा है सर उसमें सर एंगल ज्यादा है ऊपर वाले में सर देखने में तो अगर उसे क्लोज भी हम ड्रा करना चाहे तो कर नहीं सकते
देख लेते हैं ओरिएंटेशन इस ग्रेन में क्या है, ये ओरिएंटेशन ना लाइन एटम्स यहाँ इस लाइन पे जुड़े हुए हैं ना,
यस सर
तो इसी लाइन को मैं एक्सटेंड करता हुआ लेके आ रहा हूँ, क्या यहाँ पे इस ओरिएंटेशन पे है, इस ग्रेन नंबर 2 में इस ओरिएंटेशन को फॉलो कर रहे हैं?
नो सर
ग्रेन नंबर 2 में जो ओरिएंटेशन है वो क्या है, दैट इज दिस ओरिएंटेशन, ऐसे ही है।
यस सर
इन दोनों के दरमियान एंगल क्या है, दिस इज द एंगल, ठीक है।
यस सर यस सर
सिमिलर अगर ग्रेड नंबर 1 की मैं इसकी बात करूं, लेट्स से आई टेक दिस ग्रेड नंबर 3, इसकी ओरिएंटेशन क्या है, ये ओरिएंटेशन जा रही है इसकी, और इनकी ओरिएंटेशन क्या है, इनकी ओरिएंटेशन ये, तो दोनों के दरमियान डिफरेंस ऑफ एंगल क्या है,
यस सर
समझ
समझ आ गई सर
Alright. So there is this one you could the lower one you could refer to as a low angle grain boundary, this one, and the top one, this one, you could refer to it as high angle grain boundary. All right,
यस सर
great. Now you have another kind of defect in 2D defect, which is known as twin boundaries. Twin boundaries, a twin boundary is a special type of grain boundary across which there is a specific mirror lattice symmetry. That is, atoms on one side of the boundary are located in a mirror image position of the atoms on the other side. So let's see if you have this sort of arrangement. This is one arrangement. Now, if due to application of shear stress or any stress, there are some atoms that have moved to the new distances. These are the atoms that have moved to the new distance. So if you look at these atoms, there is one boundary over here. If I look at this boundary, atom on this side and atom on this side, they are, although they are the mirror images. Similarly, atom on this side is mirror imaged onto this side. Similarly, atom on this side is mirrored across the boundary at this location. This mirror image is clear to you guys?
यस सर
All right. So actually, these atoms, they are mirrored across this boundary into these atoms at this boundary. Similarly, if you look at this boundary, atoms lying on this side of the boundary, they are mirrored across this boundary into these positions. This is mirrored to this is mirrored to this, and this is mirrored to this position across this second boundary. So you have essentially two boundaries. This is one boundary and this is the other boundary, and across both the boundaries there is a mirror image. A region between the two boundaries is basically known as a twin. All right, and this is a twin boundary. So this is also a kind of planar defect where the atoms have moved from their positions, creating a distortion in the lattice, and this movement is characterized in the form of twin, which is basically a mirror image across the boundaries. And the last kind of the 2D defect that we'll be looking into is the stacking fault. That means in FCC, if you recall FCC, the stacking sequence in FCC was A, B, C, A, B, C. So there was a layer of A atoms, then there was a layer of B atoms, and then C, then followed by A, B, C, and so on and so forth. If any one of the layer is missing, so for example, you have A, B, C layer arrangement, then you have A, B, and the C layer is missing. That is a stacking fault which takes place in 2D. So a complete 2D layer is missing. That would give rise to the stacking faults in materials. A missing layer is a stacking 2D default fault. Moving on to the bulk or volume defects. Bulk or volume defects, other defects exist in all solid material that are much larger than those discussed. These bulk or volume defects, they are much larger than those discussed in the previous slides, 2D, 1D, and 0D defects. These defects include pores, cracks, foreign inclusions or foreign particles within the materials, and other phases. Other phases we'll not discuss at the moment, but once we move on to phase diagrams, we'll have a better understanding of what is meant by other phases. Uh, Now, as I mentioned, the term defect is not necessarily a disadvantage in materials. For example, the image that I'm about to show you, it's an electron microscope image, and it shows that certain defects are introduced during processing and fabrication steps in order to have the desired properties. For example, this is an electron microscope image of alumina plus CNT membrane. If you look at a higher magnification, you would see these as the CNT particles. These are alumina particles, and these black regions, they are essentially pores. So this is essentially a membrane for water purification. Water passes through this membrane and gets purified. So you need to have these certain amount of pores present in order to have a good flux of water. If there would not be any pores, the water would not be able to filter through or pass through this membrane. So you need to have strength as well as certain amount of pores as a defect in order to have a good flow of water through the membrane, as well as purification of water takes place as it passes through the membrane. So it is not necessary that pores are essentially a defect. Pores uh, could play a vital role in case of membranes, or pore control could play a vital role in case of membranes. All right. Moving on to the last half of this session, which is related to the grain size determination. This is an exercise that would help us determine the average grain or crystal size in a polycrystalline material. average grain size, why do you need it? Why do you think it is important? Because it has a great effect on the mechanical properties of polycrystalline materials, and it can be estimated from a micrograph of the microstructure. So you need to have the understanding of how to calculate the average grain size. Just to give you an idea, the smaller the grain size, the harder would be the hardness of the material, as well as the fracture toughness of the material, or the toughness of the material. We'll come to the mechanical properties in the coming chapters. But how do you calculate the average grain size? The simplest technique that you use is the average grain. To calculate the average grain size is the linear intercept method. In this method, what you do is that you draw random straight lines through the micrograph. The number of grain boundaries intersecting the lines are then counted. And to calculate the average grain size, actual line length, actual length of the line is basically divided by the number of intersections. And how do you calculate the actual line length? You divide the measured length by the magnification at which you are looking. Things would become more clear when we look into the example itself. So average grain size in micrometer is essentially 1 over number of intersections divided by actual length of the line in micrometer, or actual length of the line in micrometer divided by the number of intersections. Let's say we have this micrograph available to us. This micrograph was taken at a magnification of 200x. So what you are essentially looking at, it's 200 times magnified. This image is 200 times magnified. All right. Estimate the average grain size using the linear intercept method, assuming each line is 50 mm. So if you see at 200 mm, 200x magnification, this is appearing to be 50 mm. The line length that you see from here to here is essentially 50 millimeters. Now, the first thing is, can you identify the grains? Could you visualize different grains in the micrograph?
Yes, sir.
All right. So the first thing is I have drawn these random 1, 2, 3, 4, 5. These random 50 millimeter lines have been drawn. So I have this first line, second line, third line, fourth, and fifth line. They have been randomly drawn. And I have line number over here and number of grains intersected over here. So for the first line, I would find out the number of grains. See, this is one intersection, second, third, fourth, fifth, sixth, seventh, eighth, ninth. So I have 9 intersections for the first line that I have drawn. Similarly, I'll find out the intersections for the second line, third line, fourth, and fifth, and write down the values over here. All right. Once I have the intersections available to me, once I have found out the intersections, what I'll do is that I'll calculate the total length of the lines. Total length of the lines is, there are 5 lines multiplied by 50, it would give you 250 millimeters. Remember, this is not the actual length of the line, but is the length of the total length of the line on the figures. Is this clear to you? How would you calculate the actual total length of these lines? G, any idea?
सर सर
Yes,
इसको
sorry.
क्या कहते हैं, इसे 200 टाइम्स स्मॉलर करना पड़ेगा ना, क्योंकि 200 टाइम्स
G.
मैग्नीफाइड है.
Very good. So the actual total length would be the length of the total length of the line on the screen divided by the magnification that you have done, which is 200 in this case. So your actual length of the line would be 1.25 millimeter, which is 200x, to as 200x is the magnification. Clear enough? Is this clear?
Yes, sir.
All right. Now once you have the actual total length, you would find the number of intersections for all the 5 lines. For the first line, we find out 9, then it comes out to be 11, 9, 8, 9. So the total number of intersections comes out to be 46. Once you have these intersections available to you and the actual total length, the actual average grain size would essentially be the actual total length divided by the total number of intersections, which comes out to be 27 micrometer. So this is your average grain size for the material for which you had the microstructure. Clear enough?